Now we are going to discussing about short answer type questions under section B. The question number 11, that is, define critical angle, explain total internal reflection using a neat diagram. Now let me explain. Critical angle. When a light ray passes from denser medium into rarer medium, the angle of incidency for which in the denser medium the angle of refraction in the rarer medium becomes 90 degree is called critical angle. Let me explain. Let us consider two different media, say rarer medium, example air, denser medium, example water. From a source of light, suppose from O, a light ray is traveling from denser medium to rarer medium, which is incident at the boundary between the two media, which is called interface. Now the light ray is traveling from denser medium to rarer medium, then gets reflection, sometimes refraction. So in this case, angle of incidency is 0 and angle of refraction or angle of reflection, if you take, this is also 0. Is the situation 1. Now situation 2, from same source a light ray is considered which is incident at the interface, where we have to draw a normal. Then angle of incidence, suppose I1, which is greater than I. Now the ray gets refraction, it bends away from the normal because the light ray is traveling from denser medium to rarer medium, then it bends away from the normal, then angle of refraction is R1. Is the situation 2. Let us consider one more light ray is coming from same source, incident at the interface at one particular point, there the angle of incidence is I2, which is greater than I1. Now the angle of refraction also increases. Let us take this has to be R2, which is greater than R1. From the diagram, it's very clear. As angle of incidence increasing, angle of refraction also increases. Now consider one more light ray. Light ray is traveling from denser medium to rarer medium, incident at the interface at particular point, there the angle of incidence I am taking as I is equals to C, for which the angle of refraction means refracted ray grazes the interface, it grazes the interface, then angle of refraction R becomes 90 degree. In this case, this angle of incidence C is called critical angle. So critical angle is represented by a letter C. Now the relation between critical angle and refractive index of the medium. Let us consider denser medium refractive index mu1 is equals to mu. Rarer medium refractive index mu2 is equals to 1. Now, using Snell's law, what is Snell's law? Mu1 sin I is equals to mu2 sin R. But from the diagram, I is equals to C and R is equals to 90 degree. If you substitute these values in the formula, then mu1 means mu, sin I nothing but sin C is equals to mu2 nothing but 1 into sin R is nothing but 90 degree. So from this, sin C is equals to 1 by mu, or mu is equals to 1 by sin C. So this is the relation between refractive index mu and critical angle C. Now, total internal reflection. Total internal reflection, simply it is also called as TIR. First definition. When a ray of light passing from denser medium into a rarer medium and meets at the interface at an angle greater than critical angle C, then the light ray reflects into the same denser medium. This phenomena is called total internal reflection. Explanation. Let us consider this has to be interface, means which divides two different media. I am considering two different media as rarer medium. Example, air, denser medium. Example, glass, or you can take water also. According to the definition, light ray, say it is traveling from denser medium into rarer. The light ray is traveling from denser medium into rarer medium. Incident at the interface at particular point, there we have to draw a normal. If the angle of incidence in the denser medium is greater than critical angle, that is I greater than C, then what happens? If I is equals to C, refracted ray grazes the interface. But in this case, angle of incidence is more than critical angle. Then what happens? The ray get reflection into the same medium with I greater than C again. Because according to laws of reflection, if angle of incidence is C, then angle of reflection is also C. But in this case, I greater than C, okay, then for the reflected ray also I greater than C. So here, when ray is traveling from denser medium to rarer medium and incident at the interface at a particular point with angle of incidence greater than critical angle, then it gets reflects back into the same medium. So this phenomena is called total internal reflection. Now, the conditions to get total internal reflection are: number one, light ray must be travel from denser medium to rarer medium. That's a condition 1. Condition 2, angle of incidence in the denser medium means I should be greater than critical angle. So these are the two conditions to obtain total internal reflection phenomena. Now, uses of total internal reflection. Generally, having so many uses. Number one, optical fibers works on the basis of total internal reflection. Number two, total internal reflection is used in the construction of total reflecting prisms in binoculars. So these are the now the question number 12. The question is, how do you determine the resolving power of your eye? Explanation. To determine the resolving power of human eye, a very simple experiment. That is, make all the black strips with same width and the intermediate gap, which is nothing but white strip. So all the black strips having same width. Example, each black strip width is 5 millimeter. Like number of black strips are taken. The intermediate strip is a white part, white strip. As we go from left to right, the gap between two successive black strips is increasing in a stepwise. For example, the intermediate white strip width is 0.5 mm. The next two black strips width, gap between them is also 0.5 mm. And next two white strip width is 1 mm. And next to two white strips width is 1.5 mm each. Like that, you have to paste the black strips, okay, by maintaining the successive equal white strip widths. So this pattern is pasted on the wall in a room or a laboratory. Let us consider this has to be a room. So this type of arrangement is pasted on the wall in a room. Now, this arrangement should be at a height of an observer, eye level. Now, the experiment. By moving away or close to the wall, find the position where you can just see some two black strips as separate strips. Example, if you are observing this arrangement from your eye level by moving away from the arrangement or towards the arrangement at a particular position, you can observe this type of pattern. That means all the black strips to the left of a strip would be merged. To the left of a strip would be merged and would not be distinguishable. Means all the black strips with respect to one of the strip would be merged with each other and never be distinguishable. On the other hand, the black strips to the right of this strip would be more and more clearly visible. Okay. Note the width of merged black strips and one of the clearly visible black strip as small d. So note the width of the white strip as small d, which separates two regions. On the other hand, find the distance between the arrangement of the strips on the wall to the distance of your eye. What is capital D? Capital D is the distance between the arrangement on the wall to the position of person, means position of eye. That is capital D. Small d is what? Small d is the width of a white strip which separates two regions clearly. Then the resolution of eye is equals to small d by capital D. So this is the formula. By using this, we can estimate the resolution power of eye. Generally, one of the note point, for normal eye, resolution power of eye value is 1 minute or 1 by 60 degree. So by using this simple experiment, we can determine the resolving power of. Now we are going to discussing the question number 13. The question is, derive an expression for the intensity of electric field at an axial line of an electric dipole. First of all, we should know the meaning of electric dipole. What is an electric dipole? Electric dipole is nothing but two equal charges but having opposite sign or separated at a particular distance is known as electric dipole. For example, let us consider AB as an electric dipole. Here minus Q and plus Q, which are identical charges but having opposite signs and are separated at a distance 2a. Then this arrangement is known as electric dipole. Now, the meaning of axial line. Axial line means a line which is passing through the two charges. A line which is passing through the two charges and center of the dipole a line which is passing through the two charges and center of a dipole is called axial line. Now, this is considered as an axial line. Now we have to derive an expression for the intensity of electric field on this axial line at a particular point. Let us consider a point P on the axial line of a dipole AB. Dipole having dipole momentum. The dipole moment is directed from negative charge to positive charge. Dipole momentum is represented by capital P. Capital P formula is 2AQ. Actually, it is a vector. It is directed from negative charge to positive charge, where 2A is a vector, Q is a scalar. 2A is measured from negative charge to positive charge. Hence, dipole momentum is directed from negative charge to positive charge. Now we have to calculate electric field intensity at a point P, which is at a distance r from the center of the dipole. Then the distance from point B to point P is r minus a, and the distance from negative charge to point P is r plus a. Now, electric field intensity at point P due to positive charge. Electric field intensity due to plus Q charge at point P is, I am taking this as to be E1. E1 is equals to, what is the electric field intensity due to a point charge at a distance? That is 1 by 4 pi epsilon naught Q by R square. Now in this case, 1 by 4 pi epsilon naught, Q means here it is positive charge, no need to take sign, we have to give the direction only, Q by R square, distance square actually. From positive charge to point P, the distance is R minus A. So, it is R minus A whole square. Then this electric field due to positive charge at point P is directed from B to P, means towards right, is towards right. Now, next point, electric field intensity due to minus Q charge at point P is, I am considering this has to be E2. That means we have to calculate electric field due to this minus Q charge at point P, which is at R plus A distance. That is E2 is equals to 1 by 4 pi epsilon naught Q by distance from minus Q charge to point P is R plus A, that is R plus A square. And this field, due to negative charge at point P, the field direction is towards negative charge. That means from point P to A. So I am considering this as to be towards left. Okay. Now we have to calculate the resultant electric field at point P due to E1 and E2. That gives us net electric field, or is also known as axial electric field. Therefore, resultant electric field intensity at point P is E axial, that is equals to E1. E1 is acting towards right hand side with respect to dipole moment. E2 is acting opposite to the dipole moment direction. So one of the field direction should be taken negative. Therefore, I am taking E2 as negative. So E1 minus E2 is the resultant electric field intensity at point P. That gives us axial electric field at a point on the axial line of an electric dipole. Now substitute E1 and E2 values from these two equations. E1 is already there, that is 1 by 4 pi epsilon naught q by r minus a square, and E2 is 1 by 4 pi epsilon naught q by r plus a whole square. Substitute these two values in this equation, then we will get, on substitution of E1 and E2 values in this equation, now we will get E is equals to, E1 means 1 by 4 pi epsilon naught q by r minus a whole square, and E2 means 1 by 4 pi epsilon naught q by r plus a whole square. If you take q by 4 pi epsilon naught common out, q by 4 pi epsilon naught, remaining value, that is 1 by r minus a whole square minus 1 by r plus a whole square. Okay. Now q by 4 pi epsilon naught, here LCM r minus a whole square into r plus a whole square, then here it becomes r plus a whole square minus r minus a whole square. The next step we can write it as q by 4 pi epsilon naught. So it is in the form of a plus b whole square minus a minus b whole square. The value is 4ab, means here it becomes now 4ab means 4ar by, now it is in the form of a minus b whole square into a plus b whole square. The formula is a square minus b square whole square. That means here r square minus a square whole square. So this is the value. Now we can write this as to be, this is E axial. So E axial is equals to q by 4 pi epsilon naught. We can write this as to be 2a into 2r by r square minus a square whole square. Next we can write it as 1 by 4 pi epsilon naught 2aq, nothing but 2aq, nothing but dipole moment. So we can write it as now 2pr, where p is what? 2aq, right, by r square minus a square whole square. Since P is equals to 2aq. Okay, P is equals to 2aq. So that is the dipole moment. So this is the electric field intensity due to a dipole on its axial line. This is one of the expression. If R much more than A, that means the distance from the center of a dipole to a point where we have to calculate the axial electric field, that is R, is more than distance from the center to one of the charge of a dipole, then A square is almost negligible, that is considered as to be 0. Therefore, the above equation can be written now E axial is equals to 1 by 4 pi epsilon naught 2p r, here we will get r square whole square because a square is negligible, so it is 0, then we will get r square whole square means r power 4, but here you will get r, then r and r power 4, one of the value will be cancelled out, the remaining value is 2p by r cube. So this is the exact equation, so which represents intensity of electric field on the axial line of a dipole at a point P, which is at a distance r from the center of the dipole. So its direction, now the direction of electric field, the direction of the resultant electric field due to this E1 and E2 is always in the direction of dipole moment. So resultant electric field is directed in the direction of dipole moment. Okay, is in the direction of P bar. What is P bar? P bar is nothing but dipole moment direction. Like this, we can derive the electric field intensity due to an electric dipole. Now, question number 14. The question is, derive an expression for capacitance of a parallel plate capacitor. Let me explain. Let us consider two identical conducting metal plates. Plate P1, plate P2. Each plate area is capital A, which are separated at a distance small d. That means a parallel plate capacitor consists two identical conducting metallic plates P1, P2. Each plate area is capital A. and are separated at a distance small d. Then the gap between the two plates is filled with air or vacuum. Means the space between the two plates is considered as free space. Now, plate P1 is connected to positive terminal of an external battery. Then it acquires positive charge. And plate P2 is connected to negative terminal of an external battery. Then it acquires negative charge. Then charge on each plate is capital Q. As a result, uniform electric field is produced between the two plates. The uniform electric field is represented by using parallel straight lines which are at equidistant. But at the edges of the plates, the field will not be uniform. That will be appear like curves as shown in the figure. So this is named as fringing. This effect is called fringing. Generally, if the separation between the two plates, that is D, is much less than area of each plate, then fringing will be neglected. Now, the electric field intensity at any point between the plates is E is equals to sigma by epsilon naught. What is sigma here? Where sigma is Q by A is called surface charge density, means charge per unit area is called surface charge density of each plate. Now, E can be taken as sigma means Q by A epsilon naught. Let us take this as to be equation number 1. Now, the potential difference. The potential difference between the plates is V is equals to E into small d, where V is the potential difference between the plates, E is the electric field intensity from equation 1, okay, at any point between the two plates. Substitute E value here, then V becomes Q by A epsilon naught into small d. Now we can write this equation as Q by V is equals to A epsilon naught by d. Let us take this as to be equation number 2. But Q by V is taken as C naught, where C naught is the capacitance of a parallel plate capacitor with free space as medium. So now from equation 2 we can write this equation as Q by V nothing but C naught. So substitute C naught here. Therefore, C naught becomes A epsilon naught by D. So this is the capacitance of a parallel plate capacitor, okay, each plate area is A, distance between the two plates is D, where epsilon naught is the effect of medium between the two plates. Okay, that is permeability of free space. Now, condition. Suppose if the space between the two plates of a parallel plate capacitor is filled with a dielectric medium of dielectric constant K completely, then the capacitance with medium, any medium other than free space, can be written as A epsilon by D, or it can be taken as K A epsilon naught by D, or it can be taken as C medium is equals to K C naught, since K is equals to epsilon by epsilon naught. When a medium is introduced between the two plates completely, then capacitance increases by K times. Okay, like this we can derive an expression for capacitance of a parallel plate capacitor.